it's from 4 to 4:30. It will be the official time for posters. So, people are invited to go and look at the posters, and people who have posters are invited to speak about them here. Okay.
So we start with the afternoon session with the talk of Luis Garcia Naranjo, who is going to talk about this preservation of volumes in non-holonomic mechanics.
Okay, thanks, Hernan, for the introduction. And I would like to start by thanking the organizers for giving me the opportunity to present my work at this conference. So I'm going to tell you about my work with Yuri Fedorov and Juan Carlos Marrero, who are both here in the audience, on preservation of volumes in non-holonomic mechanics. So this is a research project that took us 4 years to complete, and we finally submitted our papers on the subject last year, so I'm going to give you a summary of our results here. So the subject of the talk, preservation of volumes in non-holonomic mechanics, I'd like to start by talking a little bit about preservation of volumes just for differential equations in general. So suppose you have a certain differential equation defined on a manifold, given in terms of a smooth vector field on it. Well, we're interested in knowing whether this preserves a certain measure. So to begin with, I need to assume the manifold to be orientable so that there exists a differential form of degree n that does not vanish. So that's going to be my volume form, say a volume form, a special one. And then I have the flow associated with the differential equation. So measure preservation is about the following. You consider a region A in space, and you're looking for a density mu, which is a differentiable function, which is positive, in such a way that when you evolve by time t all of the points of the region A, well, the region that you obtain has the same volume. So that's given in terms of this equality over here. So what we're looking for is for a density function mu, which is positive. I have to say at this point that I'm only going to be considering smooth measures. In some applications, people care about measures that are non-smooth. Well, I'm not going to say anything about those here. So I'm only going to talk about existence of smooth invariant measures. So the infinitesimal version of the measure preservation is the following. If you take the derivative of the evolution of the volume at time t and evaluate at t equals 0, then what you get is the integral over the region A of the divergence of the density m times your vector field f. And you would like that integral to be equal to 0, which means that the volume is preserved. And so you get the following infinitesimal condition. So in this equation, mu is your unknown, which is the density. F is known, is the vector field. And the volume that you fixed at the beginning, that would be nu. So this is called Liouville's equation. And in local coordinates, this is the PDE for mu. So, in a sense, if we look for an invariant measure, what we're looking for is for existence of a global solution to this equation. And let me insist on the fact that the solution that we're looking for is global, because locally, the flow just looks like straight line motion if you're far away from an equilibrium point. So locally, every system preserves a measure. So we're looking at a global aspect of the flow. Okay, so what's the importance, or why would we care about something like that? So there's motivations in integrability of systems. That's a reason why you would care to have an invariant measure. But in this case, I'm talking about non-holonomic systems. I'm going to say that my main motivation is that if you have a preserved measure, then that's an obstruction for equilibriums that are asymptotically stable. So you cannot have this type of situation where everything comes into an equilibrium point, or you cannot have something where you have a periodic orbit which is asymptotically stable, so things are approaching it asymptotically. And I put here a picture of the famous rattleback that has an attractive periodic orbit. So existence of an invariant measure would be an obstruction for this kind of behavior. So that's an important reason why we would care about studying this problem. So a system that you all know that preserves a measure is symplectic Hamiltonian systems. So suppose that the vector field is given in terms of a symplectic form and the differential of a Hamiltonian through these equations that you're all acquainted with. Well, then Liouville's theorem for Hamiltonian systems tells you that the measure omega to the power m is preserved, where m is half the dimension of the manifold. And this is really a consequence of the fact that the flow of a Hamiltonian vector field acts by symplectic transformations. Now, the problem is that non-holonomic systems do not fit into this framework, so the question of whether they preserve a measure or not is a little bit harder to answer. So another type of problems where you can fully give an answer of whether there exists a preserved measure or not is the following. And this is a very important example for our purposes. I mean, this is the heart of our results in a way. If your manifold happens to be Rn and you have a homogeneous equation of degree k, so homogeneous means that the vector field satisfies this type of condition. If you multiply the argument by lambda, then lambda pops out to a certain power k. Then Kozlov studied this problem in 1988. I came up with the following observation, which is really important for our purposes. So the fact that I'm working on Rn enables me to talk about the Euclidean measure. So what Kozlov noticed is that if there is a preserved measure at all for this system, then necessarily the preserved measure has to be the Euclidean one. Okay? Any density that you put in front of it has to be a conserved quantity. So the statement of the result is over there. It preserves this measure mu of x dx if and only if it in fact preserves the measure dx, which is the Euclidean measure, and mu of x is a conserved quantity. Okay? Now, the proof of this fact is really simple, and it's at the heart of our results, as I've said. So I'd like to just walk you through the proof in a short way. So since mu, this density, is positive, I can take its logarithm sigma and write it as mu is equal to e to the sigma. Now, the condition that the divergence of mu times f is equal to 0, I can write it as divergence of e to the sigma times f equals 0. Now, if I use the product rule and identities from vector calculus, well, this is the derivative of sigma along the direction of f plus the divergence of f, all of it multiplied by e to the sigma. But e to the sigma cannot be 0, so therefore this thing has to be equal to minus this thing, which is the gradient of f. I mean, the derivative of f along sigma has to be equal minus the divergence of f. But now I use homogeneity. So by homogeneity, the right-hand side is homogeneous of degree k minus 1 because I've taken one derivative of f, whereas the left-hand side is homogeneous of degree k. So the only way these powers can balance, if sigma is a smooth function, is if both terms vanish independently. So the vanishing of the gradient of sigma dotted with f means that sigma is a preserved quantity, which in turn implies that mu is a preserved quantity. And on the other hand, the conditions that the divergence of f is equal to 0 means that the Euclidean measure was preserved. So this simple calculation is at the heart of all of our analysis. Okay, so let me tell you how this works or how this is useful to study what I'm going to call Lie-Poisson mechanical systems. So I'm going to think of systems which are defined in terms of a linear, almost Poisson structure. So linear almost Poisson structure means that the matrix that I have over here that defines the bracket is Q-symmetric and its sentries depend linearly on the coordinates. So I'm working on a vector space, so this makes perfect sense. So these coefficients are supposed to be skew-symmetric in the lower indices. And then one thing that might hold, or I'm going to allow myself not to hold, is a Jacobi identity. And I'm going to allow myself for the possibility that this doesn't hold because I'm thinking of applying this to non-holonomic mechanics. If it does hold, then these coefficients make Rn into a Lie algebra. So the Hamiltonian systems are defined just by multiplying the matrix pi by the gradient of your Hamiltonian, so that is the Hamiltonian system. And I'm interested in considering what I'm going to call mechanical Hamiltonians. So mechanical Hamiltonians are going to be things that are quadratic on the coordinates, and the coefficients are symmetric and positive definite. So think of it as an energy, right? So these are the coefficients of a certain kinetic energy. Now the important thing of it all is that if this is a linear Poisson structure, then pi is linear. And if h is quadratic, when you take its gradient, you get something that's linear. So when you multiply linear times linear, what you get is something that is quadratic, right? So I can apply the result of Kozlov to analyze preservation of measure for this system. So that's the system written out in coordinates, and I'm wondering whether it preserves a measure. So by Kozlov results, I know that I should only be worried about it conserving the Euclidean measure. So if I take the divergence with respect to the Euclidean metric, well, what I end up with is two terms coming from the fact that I'm differentiating something that's quadratic. And one of them is going to vanish due to the skew symmetry of the coefficient C on the lower indices and the symmetry of the coefficients K that define the quadratic form. And what I'm left with is an interesting term that involves this term C alpha, lower alpha, upper alpha. So there's a sum over there multiplied by times this coefficients K times X. Now, if there's a preserved measure, this is going to vanish for every single choice of X. Okay? Now, since the matrix K is non-degenerate, the only way this can happen is if these sums are all equal to 0. Okay? So this is a well, it's actually a necessary and sufficient condition that only involves the coefficient C for the preservation of a volume. Now, if we were really talking about a Lie algebra, meaning that the Jacobi identity held, then these conditions actually mean that the Lie algebra, the underlying Lie algebra, is unimodular. So this is the first instance in which we see a relationship between unimodularity of a structure and the preservation of volume. So I just want to push this idea further ahead. Okay? So pushing it further ahead means I'm going to consider almost Poisson structures that are not necessarily linear on the entries, and this is the degree of generality that I'm going to need for my examples in nonholonomic mechanics. And so the matrix pi is not linear in the entries, but then it's Q-symmetric, and then the Jacobi identity might hold or it might not. Hamiltonian vector fields are defined in the same way. You multiply this matrix times the gradient, and you end up with your vector field. And here are the entries written out explicitly. Now, if I wonder whether this system preserves the Euclidean measure, well, I take the divergence of it, and I have two terms again. One that comes by differentiating the entries of pi, and one that comes by differentiating the derivatives of h. Now, the term that involves the second derivatives is going to vanish just like before. What happens is that this term is symmetric in the coefficients, in the indices alpha and beta, by equality of mixed partial, whereas the other one is going to give something that just has first derivatives of h in it. So I can write this as the evolution of h along a certain vector field that I'm denoting by script m. And this vector field, script m, that does that game, I'm going to call it the modular vector field of the Poisson structure, and to be precise, I should say, with respect to the Euclidean measure. Now, I'm considering whether, here I'm just making a calculation to see if the Euclidean measure is preserved, but if I'm really studying the problem of preservation of volumes, well, I should consider more general measures, because nobody tells me that this system that I'm studying is homogeneous of any degree. So if I just take the divergence along with a more general density over here, so I multiply by a positive function, what you end up getting by using the product rule is you get a term that involves the divergence of xh, which gives me something involving the modular vector field that I introduced in the previous slide, and then I get something that involves the derivative of sigma along xh. But this is Hamiltonian-like, so if I take the derivative of sigma along xh, that's exactly the same thing as taking the derivative of h along minus x sigma, right? Just by skew symmetry of the Poisson bracket, or the almost Poisson bracket. So what I end up with is a correction of the modular vector field by a Hamiltonian vector field. So this is going to be the motivation for the following definition. I'm going to say that the structure that I'm studying is unimodular if this vector field that I've introduced here happens to be Hamiltonian. That is to say, it is equal to x sigma for a certain sigma. Now, this definition makes the following observation trivial. Unimodularity is a sufficient condition for the existence of an invariant measure, because the vector field that does this trick is giving me the logarithm of the density of the preserved measure. So that's just obvious. Now, what's not obvious is the other implication. The other implication is that in some cases, like the one I presented before, where the structure was linear and the Hamiltonian was quadratic, then the condition is also necessary, meaning that unimodularity is equivalent to the preservation of a volume. So that implication is not at all trivial. Now, what I want to say here is that this definition of unimodularity and the conclusions that I just drew out of it only depend on the skew symmetry of the structure. I have not used the Jacobi identity. If you use the Jacobi identity, then you can talk about modular classes of Poisson manifolds and things like that I do not want to get into in this talk. So here's a summary of what I've told you so far. I have this concept of unimodularity, and it implies the existence of an invariant measure. and in some cases, the existence of an invariant measure implies unimodularity. So it's a way to characterize existence of measure for a particular types of system. The discussion that I've done so far is I have done it in vector spaces, assuming that the phase space manifold was Rn, but it can be generalized to orientable, almost Poisson manifolds. And an important fact of it all is that unimodularity is a geometric constant that is both global and intrinsic. Okay, so it does not depend on coordinates, and it addresses the behavior on the whole phase space manifold. So it is an adequate geometric object to study measure preservation. Okay, it contains the two aspects that are really important, which is globality and the fact that it's intrinsic. Okay, so enough of the theory. Let me go to the equations that I want to study. So the equations that I want to study have this form over here. So the important thing here is that Q's are going to be variables on a configuration manifold, big Q, and the P's are going to be coordinates on a vector space. They are quasi-momenta. And you can all recognize this universal form of the equations. So many, conservative systems with finite number of degrees of freedom can be written in this way. Before reduction, after reduction, Poisson systems. It's a very universal form of the equations. And people who know about algebras will appreciate the fact that I've used rhos and cis in my notation over there. So, as I've said, Q's are configuration variables, P's are quasi-momenta, and I'm going to think about Hamiltonians that are quadratic on the P's and, with coefficients that depend on the Q, meaning that I only have a kinetic energy. So that's what I put over there, kinetic mechanical system. So I have no potential, okay? Now, I do have skew symmetry of the coefficient C, and then the Jacobi identity involving the rhos and the C's might hold or it might not. Now, the crucial observation now is the following. Since H is quadratic, the equation for P's, and the P's move on a vector space, is homogeneous of degree 2. So what I have on the right-hand side, derivatives of H with respect to Q are going to produce terms that are quadratic on the P's, and then I have here something that's linear on the P's multiplied by something that's linear on the P's, so that produces also something that's quadratic. So I have something that's homogeneous of degree 2. So what we did was just extend Kozlov's observation of systems that are homogeneous. So this equation is homogeneous of degree 2 in P. And what you end up with is saying, well, if you have an invariant measure, then the density that you have to put in there only depends on the Q's. Only on the Q's and not on the P's. So that simple observation is important. So this system of equations, being conservative, can be written in terms of an almost Poisson structure that has the following form. So here I've written it out in blocks. So there's a block that only depends on Q's, this Q-symmetric correspondence over here, and then the terms that depend on P are linear, okay? So I have somehow a linear Poisson structure over there. And this is our main theoretical result, unimodularity of this kind of structures with a quadratic Hamiltonian is equivalent to the existence of an invariant volume, which in turn is equivalent to the existence of an invariant volume with a basic density, meaning that the density does not depend on the P's. So, as I've said before, the implication to the right is trivial, but the one that's non-trivial is going to the left, okay? Now, if you look at the unimodularity condition, well, you ask yourself whether this vector field is Hamiltonian, and you end up with a system of partial differential equations, so it doesn't seem like you've accomplished much, because Liouville's equation to begin with was given system of differential equations, of partial differential equations. So what have we accomplished? So at this point, really nothing. But if you look at non-holonomic systems with symmetry, this is where it all becomes useful. So by non-holonomic system with symmetry, I'm thinking of a non-holonomic system for which the constraints and the Hamiltonian, which is pure kinetic energy, are invariant under the action of a Lie group. So in this case, I can pick the P's that were quasi-momentum as coordinates that correspond to quasi-velocities that are either transversal to the group action or compatible to the group action, meaning some of them are going to be tangent to the orbits, the corresponding quasi-velocities, and the other ones are going to be transversal to the group orbits. So with this choice, and there's certain technical details that I'm avoiding here, talking about a certain rank condition, and there's a choice of a connection, what you end up with is you end up with a reduced Poisson structure of the same kind, except that the fact that you put something blue here, meaning something compatible, make some zeros appear on this part. And these zeros are going to be extremely important. And the Hamiltonian can be written in block diagonal form with respect to the choice of momenta that were going in the two directions, transversal and tangential to the group orbits. So the unimodularity condition is going to contain a part that involves derivatives of sigma, so sigma is an unknown over here, but then the blue part coming out from the compatible directions with the group orbits is going to produce something that's just a functional relationship on the variables q equal to 0. And if this is not equal to 0, what you find is an obstruction for the existence of an invariant measure. So what we did is apply this sort of technique, this technique to many systems with symmetry, and this gave us conditions on the coefficients that appear in the equations in order to have a preserved measure. So this was sort of obstruction that we sort of went around. And then I should say that this approach of us unifies and generalizes results in the literature, some of them by Kozlov, Jovanovic, Kantrigin, and co-authors, David Martin and Manolo, Dmitry Zankov, and Tony Block, who had also made progress and obtained certain conditions or in more particular setup. Okay, so based upon these, we were able to find an algorithm to study the measure preservation of a non-holonomic system with symmetry. So the important thing was to compute the coefficients that enter the unimodularity conditions. To do so, what you need to do is to construct a G-invariant basis, so a basis that's invariant under the group action that spans the constraint distribution, and you split it in two. One that is tangential to the group orbits, this is G-vertical, and one that's transversal, okay? The one that's transversal is going to define the coefficients rho over here that enter the unimodularity conditions. And then what you need to do is to take their commutators and project using the kinetic energy metric. So when you take commutators of these vector fields, you stick out of the distribution because you're non-holonomic. Then you project back, and you can write what you get in terms of the basis. And those coefficients are the C's that enter the unimodularity conditions. So then you just examine these conditions. So let me tell you how this works for specific examples. So the first example that I'm going to talk about concerns this problem. So you have a sphere that's fixed, and then you have a body, a rigid body that has a flat face that's rolling over that sphere and moving under its own inertia. So think of this as a shoe, for example. So it's moving under its own inertia, but subject to the condition that it's rolling without slipping. So if you consider this problem, there's a symmetry, and that is that you can give the orientation that you wish to the underlying sphere, to the support sphere down here. So there is an SO3 symmetry. And out of all of the rotations that you can do of this sphere, there's a very particular one that has axis OP, because if you rotate about that axis, you do not violate the constraint. You're simply spinning. So that gives you the compatible direction with the constraints. So associated with that direction, there is a functional relationship that needs to be satisfied in order to have a preserved measure. So if I write it down, I get the following expression where Q1 and Q2 are the coordinates of the contact point P with respect to this body fixed basis. So the necessary condition for the existence of an invariant measure is that this thing over here vanishes, which is a polynomial in Q1 and Q2. So in order for this to vanish, I need all of the coefficients to vanish. And the vanishing of the coefficient gives me the following conditions on the inertia tensor. Namely, it needs to be diagonal. And then here I get a very interesting condition which tells me either I11 is equal to I22 or L is equal to 0. And L here is the distance between the center of mass and the flat face of the body. So then this system that I've written out over here has a preserved measure only in two situations. Either the body upstairs is axially symmetric, or if it's flat. Okay? In any other situation, it won't have a preserved measure. Another problem that we were able to study with our method is the following. Consider an inhomogeneous sphere rolling on the plane. Now I'm assuming that the center of mass need not coincide with the geometric center, so some people call this the Chaplygian top as opposed to the Chaplygian sphere where the centers coincide. So here you're rolling on the plane, so you have an SE2 symmetry, and again you have one compatible symmetry which with the constraints which corresponds to just rotating and rotating the plane about the point sitting just above this geometric center of the sphere. So if you write down the condition that you get, you wound up with the following conditions. For the existence of a preserved measure, the following needs to be true. Either the center of mass coincides with the geometric center, which is the case studied by Chaplygin, where he gave the explicit formula for the preserved measure, or the other possibility is that the distribution of mass on the sphere is actually symmetric. Okay, so you have a symmetric distribution of mass within the sphere. Another example concerns the rolling of a homogeneous ellipsoid on the plane. So this is an ellipsoid. The distribution of mass inside of the ellipsoid is uniform, and it's rolling without slipping on the plane. And the condition that you obtain using our method tells you that if there is a preserved measure, then necessarily two of the semi-axes of the ellipsoid are equal. So you're really talking about a solid of revolution. Okay. I also considered, we also considered this problem of the rolling of a ball that's inhomogeneous outside of a cylinder. The reason why we did this is because this is so-called example. It's an example of a so-called Chaplygin system, and what we obtained is that there is an invariant measure if and only if the sphere is homogeneous. And then we also considered the limit when the cylinder went to a point. I mean, the radius of the cylinder went to 0, which corresponds to a ball rolling on a wire. The reason to do this was technical. It's because that system does not satisfy the so-called dimension assumption. So for technical reasons, it's an example that can be treated, say, with our methods, but not with existing results in the literature. And what we found is the same thing. There is an invariant measure if and only if the ball is homogeneous. So to end up, I want to make a slide about Jair's input on our problem, because I think that many of Jair's work on non-holonomic mechanics has been useful for us to arrive at this. So first thing that I'd like to mention is Jair's work on reduction. So his paper back from 92, I mean, he started talking about the relationship between the constraint distribution and the tangent space to the orbit. So when I was talking about directions that are compatible with the constraints or not, I'm really talking about this thing that, I mean, was pointed out a long time ago by Jair. I also want to say that he has done systematic work on Hamiltonization of G-Chaplygin system and its relationship with invariant measures. This paper that appeared in Alan Fest's proceedings talks a lot about that. Another contribution, important in my opinion, is he's always stressed the importance of moving frames, the use of quasi-velocities and quasi-momenta to talk about non-holonomic systems. So I've mentioned here two papers. This one, moving frames for cotangent bundles, I found it very educational for myself, and he also talks a lot about it in these proceedings. And he's also talked about concrete examples. So, studying rubber rolling has been useful, and in this paper in Regular Chaotic Dynamics 2007, he has explicit formula for rubber rolling over a sphere that's very mysterious, involving the radii of both spheres in a very interesting way. So I'd like to finish saying that, Jair was external reviewer in my dissertation, and ever since he's been very supportive, and I think that many mathematicians in our generation are very thankful for his support and how much we've learned from you. So I'd like to say congratulations, Jair, and thank you to you all.